Okay, so we are welcome to the class. So following what we promised last week, we continue with the discussion on the prediction of generalized anxiety levels during COVID-19 pandemic, a machine learning-based modeling approach. So published in Informatics in Medicine Unlocked, and those are some of our authors. A lot of them are members of our platform here. So we looked into the aims and objectives last time, which is want to classify anxiety during the COVID-19 into either is there anxiety or no, yes or no. And then the second one was to also look into the level of anxiety. Is it low, medium, or high? So those are the two kind of, one is binary classification, that is having two classes, while the other one is three-class problem. So we look into how this can be done. Hopefully that will make it possible to quickly diagnose who is having anxiety or otherwise. So we discussed the machine learning method that was explored, which are the support vector machine, and also the justification for it were provided, which is very important when you write. Why do you think out of several other methods, this is the algorithm you are selecting? We need to mention it. So we described this last time. We also look into the description of the data set that were used, 20 attributes. So later feature selection was carried out. We also mentioned that experimental setup is very, very important. You need to mention how you set up your experiment, because anybody reading your experimental setup should be able to reproduce your work. If your work is not reproducible, that is a very big weakness, and one of the reasons why reviewers do reject papers. So they want to see, can someone reproduce what you have done? It means you need to provide as much as possible details without going to unnecessary details, by the way. So that will make someone to be able to reproduce your work. You have to tell us, of course, the algorithm you are using, the percentage split. Are you using tenfold, or you are using direct partition? Things that if you don't tell us, there's no way someone can know. However, you don't start wasting time telling people how to download Weka, how to start Weka. No, this is not part of experiment. Anybody who wants to do experiment will know how to do that. However, information that if you hide the information, no one can know it. For example, you didn't tell us the parameter value. So we also talk about the optimization of the parameter. You see, here now we can see that for the support vector machine, we use a polynomial kernel. It has to be clearly stated, because if you don't tell us you use polynomial kernel, there's no way someone will know what you have used. It means the experiment is not reproducible. So these are very important stuff that needs to be made very, very clear in our report as we write our experimental outcomes. So we stop at this point. I remember last week, we tried to talk about the feature selection. Sometimes, like we say, we let the data speak. So immediately you get your data, you don't go to feature selection, or you do the experiment and see. Maybe reason for feature selection include, we want to reduce the computational complexity. Because imagine you have a medical, a kind of a medical project that people need to go and do laboratory tests up to like maybe 20 or 15. That's going to be a big fund. Even where it is free, it's going to be a big burden on the government that is making such tests free. So can we reduce from 15 to like 3 or 5 and still get the same accuracy? That is the idea of feature selection. So feature selection is not only to improve the accuracy, but sometimes you might even have achieved 100%, but you're achieving 100% using 20 variables. To gather 20 variables for subsequent prediction is very challenging. Can I bring it down to 10, 3, 5, and still get the same 100%? If we can do that, why not? Because it's cheaper and easier to get or to gather fewer number of features. See? So this is very, very important. Now, so in this experiment, this work, feature selection was carried out for the two-class problem. They were able to identify which of the, how many features will produce the best result for us. The same thing also was done for the three-class problem. So to also see, because sometimes you could see that by having 3 classes or 2 classes, that could be total different in the outcome. I mean, in the kind of number of features that will really determine the best one to be selected. Because binary feature selection, binary classification problem is simpler, just 2 classes. It's like yes or no. When it becomes 3, then we are classifying them into more than 2 classes. Of course, it becomes a little bit more challenging, but still better than more. The more the number of classes, the more the challenge that is involved. So, and then also you have the final models for the 2 class problems. You can see some of the results. Support vector machine is clearly leading with up to accuracy of 100%, precision, recall, F measure. These are the quality measures for classification that have been selected for this work. While decision tree, the version of decision tree in Weka is known as, very popular one is known as D48. Also not too bad, it's not bad. This is 95.96 and the precision 97%, so getting closer to also support vector machine. So support vector machine is really very powerful, very simple. Like I said, we should look out to the video that I'm going to upload something for us that will describe support vector machine. Pending the time, we're going to also discuss it together in a weekly program. So it's a very, very powerful machine learning algorithm with a very unique attribute that made it to be so. So we're going to look into that one later on. So this is the outcome, where we also have the confusion matrix. We've discussed confusion matrix, one of the way, if you are dealing with classification problem, it makes it easier for us to know what is the output, what is the actual outcome of this particular experiment. You can see here that you have the actual, then you have the predicted. This is anxiety, this is non-anxiety. This is 2 class confusion matrix. So this is, we call this true positive. True positive means those people that have anxiety and the system predicted them to be having anxiety. We call them true positive. That's 2,425. Then true negative, those are those people, they don't have anxiety and the system also predicted them that they are not having anxiety. And that is 592. You see, then we have these false negative. Those are the people that ordinarily, false negative means they are supposed to be positive, but they are predicted to be negative. And then we have the false positive here. They are not positive, they are supposed to be negative, but they are predicted to be negative. But because support vector machine achieve 100% accuracy, you can see here it is 0, 0. It means there was no mistake. You see, this will bring us to another issue then. Because when we look at the data, you see that the data is imbalance. The number of samples on the other side is more than the one in the other side. We try to look at, sometimes if the data is not balanced, that could actually affect our work significantly. But sometimes you see some algorithm, or depend on the data set, they deal with it without any problem. And that's why I recommend for people, once you have your data, let the data speak. Don't waste too much time. Some people, the moment they see data set, we want to handle missing value, we want to handle. You don't need to do everything. You might end up mutilating your data that you are not dealing with the original data anymore. So plug in your data into the system. The moment you get the data, let's see what you can get. Maybe your algorithm will really be able to figure out what is inside your data, and you get all the performance measure came out excellent. So what is the issue there? The other one is going to be optimization. We want to make it better. We want to reduce the number of features for computational complexity reduction. Those are other issues. But it's always good to, first of all, let the data speak. Put your data into the system. Let's see how far you can go. Because sometimes I've worked with several of my students have worked with imbalanced data, and the algorithm was able to solve the imbalance problem with excellent results. So why going for missing data, for imbalanced data treatment, when the algorithm is able to do it? And the prediction for both training, testing, validation, they were all excellent, because it depends on the data set. You could bring a data set that has imbalanced data. It means imbalanced data means one class is having like 1,000 samples. The second class is having just 200 samples. So it means we have 1,200 data samples. Some algorithm will not be able to solve it. While some will solve it without any issue. So first of all, we use the original data must be used before we start manipulating the data and try to see what can we do. However, when we use the original data and we are getting really bad results, then we have to start, okay, what can we do? It's stage by stage. Then for the second one also, supervised machine still taking the lead. So, and then we're going to now look into, like I said, now we are going to look into the practical application. How did we really carry out this experiment? Now, this is our Weka. So that's why I'm sharing my full screen. You can see it. This is the Weka. As you click the Explorer, so you click the Explorer, we are going to deal with the Explorer. So this will open for us, the Explorer window. So in the Explorer window, the first thing you can see that everything is gray out. So we have videos already that describe how to work with Weka environment. So you need to open your file. And what is that, your file? You first of all need to make up your file. That file needs to be in Excel. You see, this is the anxiety category. This is a CSV file. So put your data in Excel, save it as CSV. See, when you want to just save as, this is very important. So you have to choose the option. You have to see different way you can see. This is CSV, comma delimited file. This is the option we are using. So once you put your data in Excel, you save it as CSV, it's easier. You can easily upload it into your Weka environment. Otherwise, Weka has its own special file, this ARTF format, but preparing that format is very challenging. If I don't recommend it for anybody to do that. So you can just prepare. Excel is a common thing for all of us. Just put it in Excel, save as CSV. Then when you load it to Weka, then you can now save your data into ARTS format, whatever format. Weka will prepare that for you because already your data is inside the Weka. So the very simpler way to do is to go by the Excel. Now, so this is the data. You can see this is the first attribute. As usual, this is first question. These are some of the questions that are considered relevant to this work. Yeah. So this is the region where the person came from, and then this is the category. The category is this what we want to predict. Is either 0 or 1, because this one is for yes or no. Is there anxiety or no anxiety? Is there anxiety, no anxiety? The second experiment is going to try to investigate what is the level of anxiety. Is it low? Is it medium, or is it high? But for this one, it is like a yes or no. That's why you have here 0 or 1. 0 or 1. If you like, your data could be yes or no. It's okay. See, just like when you are solving classification problem with Weka, then in that case, this category, this is the one you want to predict, need to be in not a continuous variable. I mean, not a continuous value. So you have to use discrete value. Either you use yes or no, yes or no. You don't put 1 0 1 0. It will consider it as if you are solving regression problem. You see? So, but your attribute can be any value here. It can be 0, 1, can be any value, it doesn't matter. But your target need to be categorical. Is it yes or no? Is it 1, 2, 3, 4? This is how it will differentiate between your target and the other inputs or the attributes. Now, having said this, now let's go back to our Weka. So you open the file, you try to locate, you can put your file anywhere you want. So click open. So I have to go and locate my file. So I think this is it's either this folder, yeah, Adam's archive, and the seminars, ML. Then this is paper presentation. This is anxiety paper, yeah. So in the anxiety paper, I have anxiety paper data set. See, you can see nothing is there. See, because why? Because my Weka is trying to locate data with .arff format. This is the original format for Weka. but I didn't store my data in this format. I store my data in CSV. So I need to go here and check. I have to say, okay, I have to select the option here, file type, CSV data. So I have to click CSV data files. You can see now my data now pop up because they are there already, but you couldn't see it because it's not in the format. Now I can open my CSV. So the first thing, I have 4 files here. This is anxiety category feature selection. This is after the feature selection. This is not the one. We are not starting with that. This is anxiety category. This is the one we want to use. See it? It's anxiety score. No, that's the one with 1, 2, 3. Now this one we want to work with. So I'm going to open this file. Yeah. You can see the moment you open your file, all the functionality here, and they become active. They were gray out before. You see, because we cannot click down until you load the data. That's the first step. Now my data is in, so you can check. Usually, when you arrange your data in Excel, I always tell people, let your target value, the one you want to predict, let it be at the last column. Because we can automatically consider the last column as the class. But if you put the values, the attribute to be predicted, if you put it as number 1, you have to manually tell Weka that, no, this is my own target value. So which sometimes you might forget to do. So I always tell people, put your class to be predicted, put it as the last column. So automatically when you open your Weka, you see it there. This is the category. And once you click each of them, it can tell you the distribution. You can see this is made up of, in this category, you have 2 options. It's either 0 or 1. 0 means no. Yeah, the other one means, yeah, 1. That this is 0 or 1. This is the total count for 0. That is 2, 2, 4, 2, 5. For 1, it is 5, 9, 2. It means the class is imbalanced. Even you can look at the visualization here. See, this one is very few. This one is much, 2,000 plus. We call this kind of problem data imbalance. But sometimes, depending on the nature of the data set, when you have this kind of data, 2,425 against 592, this is very imbalanced. It means that one class is more than the other class. Usually, we want to be very close together, even if they are not the same, but the gap should not be much. But now the gap is much. And this is real life data. But okay, let the data speak. Let's try and see what's going to happen. Sometimes because of the nature of the data set and the algorithm, the algorithm might be able to understand the data and you still get excellent result, even without balancing the data. That is fine. But some situations, you just run the experiment, you do optimization, you do everything, feature selection. No, you are stuck with 50% accuracy. In that case, it becomes compulsory for you to solve the imbalance problem. And there are different ways of solving imbalance problem, which I think we're going to discuss that one on another day, inshallah, because another topic on its own. But sometimes of recent, I've been seeing a lot of very excellent data say that even with imbalance, the algorithms still were able to model it excellently well, without any trouble, without any problem. Now, and I think this is also the case of this data we are dealing with. So now we can see here the data distribution. This is the target. You can check for others. This is a region. So you can see different ones. You can see these are just, our major thing is here. This one has to be unique because we are only predicting 0 or 1. But for others, they can take any value. Now, the next thing is for you to select classify. What is the classifier that you want to use? You need to select this classifier. You need to select classifier. There are other, this is clustering, this is association, and other attributes, other functionality. This is Weka is here. So here we need to select the classifier. This is where you select your algorithm. Now, to select the algorithm, we have to go here. Look at here, choose the algorithm. And then if in this experiment, we use support vector machine, you will see support vector machine inside this function. You can see different one here. This is tree. You can see tree is here. Anything like decision tree, random forest, they are inside this tree. So, okay, let me first of all start with J48. J48 is here, so I can select it. I can select J48, and I can also select start from support vector machine. So this is support vector machine, SMO. See, support vector machine, the good thing, it also has different variants. So what I think the one used here is SMO. So there's another one here, live SVM. It's another implementation of the same SVM, support vector machine. So we go for SMO. I think that was what was used. So now we have selected the algorithm that we want to deal with. Now, the next thing is when you select the algorithm, it came with default values. So we're going to start with the default value. If you want to see the default value, just click here. You see the parameter. These are the parameter of SVM. The most important parameter in SVM is the kernel function. You can see the kernel here. It is originally set to polynomial kernel. The next important one is C, which is regularization factor C. It is set to 1. So this are the default parameters. Epsilon is set here. So these are the hyperparameters. Others are parameters that are just for programming sake. You see, like the random seed. If you are generating data partition, you want to know the seed, you fix in so that you can be, anytime you generate your data randomly, you want to be getting the same value. So they are not part of the parameter for your algorithm. That is why we differentiate between, this is hyperparameter, this is just ordinary parameter. Random seed is ordinary parameter. Number of fold, number of decimal places. These are just parameter. Number of decimal places, you are setting how many decimal places do I want to have my result in? Is it 2 or 3 or 4? This doesn't have anything to do with our algorithm. But those that will affect our algorithm, they are called hyperparameters. And they are a kernel, C, epsilon. You see, the batch size, all those ones, these are just parameters that could be ignored. They have been set to their own default. So we'll start with the default value. Then later we'll try to see what optimization can produce for us. This is for the algorithm. We have selected our algorithm, SMO. Now, the next thing you need to decide, how am I going to divide my data? Data partitioning is very important. When you are developing machine learning experiment, you have to divide your data into some parts. You don't use all the data at the same time. And then we have 2 major ways of dividing it. The first one is known as percentage split. This is called hold-out method. Hold-out method. See, some people call it direct partitioning. You just partition your data into 2. So I can select this option. In that case, I'm going to specify the percentage for training. Default is 66% for training. I want it for 70%. I think the experiment used 80, if I'm not mistaken. So we want 80%. We want 80%. Then the remaining 20% automatically becomes for testing. So it's going to use 80% for training, and then it will keep the remaining 20% for checking the outcome of your training to see if your model is able to identify the samples to be checked later on. However, this is the second option is what we call the cross validation. We double check. So in the experiments we are discussing, let's see what was used there. It was 10-fold cross validation. Yeah, it was 10-fold cross validation. So we were trying to repeat the experiment. So we utilize that one, but then that's fine. Yeah. So it is 10-fold cross validation. What is 10-fold cross validation? I think there's another video for this. So because of our time, but just to remind us, in 10-fold cross validation, you partition your data into 10 places. See, you need to divide your data into 10 places. So let's say the data is made up of 1,000 sets. So divided by 10, there's going to be 100, 100, 100 in each of the partition. So the system, we use the first 90, the first 900. That is combine 100, 100, 100 in 9 places to train. You use the 900 for training. And then the remaining partition, which is 100 samples now, for the partition number 10, it will use it for testing or validation, as the case may be. Now, it to do the experiment second time. This time around, the one that was left out for testing will be brought back as part of the training set. One of the first 9 will be removed and kept secret as they want to be used for checking, which is it is now the testing set this time around. So to do this 10 times, each time is going to be using different partition for testing. So when you have the 10-fold cross-validation, it's going to run the experiment 10 times, and each of these time it will be using different partition for checking the results. Combine 9 portions, test it using the extracted 10 portion. Bring the 10 portion back into the system, and then continuously until it runs it 10 times. The advantage of this, some people so much believe in it, that it want to make sure that you use all the data samples as testing set at least one time. So they want to be sure that your result is not random. They want to be sure your result is not random. Because for those people who just divide your data into 80%, it means this 80% of the data will be used for training. They will never be used for testing. They're not going to be used for testing set. Only the 20% reserve will be used for testing. So this is why some reviewers will say, okay, but this is, why don't you use cross-validation? But however, what you do is to explain to them, these two are established way of developing models. Either you use percentage split or use cross-validation, you are correct. For me, I've never had to repeat my experiment because of these differences of opinion. You just need to explain to your reviewer why you have used this option. And any of the options you use is valid. However, if your data is really very few, very small, then cross-validation becomes the only option you are going to have. Imagine I'm having only 16 values. So out of 16 values, 16 samples, how am I going to, 80% of 16 will be very small for partition training, and that's keeping it for testing. In that case, I'm going to use cross-validation. If there is a special case of cross-validation that we call holdout, that is, you hold only one out. It means every member of that particular sample will be used as training set at any point, as testing set at any point in time. If I have 16 values, I've used 15 for training, only 1 for testing. I use another 15, another 1 for testing, if your data is really very few. And that is why this one, you can make your cross-validation to be 10. It could be 5. It could be 3. That is the number of partitions you want to check, how many places you want to partition data to, depend on the data size. So if data is very small, cross-validation becomes a very good option for you. But if your data is sizable, then you go for percentage split. So for this experiment, we have the freedom to use any of the two. Either you use partition because the data is sizably okay, or you use the cross-validation, but the cross-validation has been used. Like I said, some people do believe in it much. Now, we have selected the cross-validation, and we have selected the algorithm, and the parameter is set to default. The next thing for you is to click Start. Start. It's done so fast. We can see here that this is the correctly classified instances, 99.6%, 3,000 plus are classified correctly. There are 11 incorrectly classified. These are the error. So you can see this is the confusion matrix here. It gives you the confusion matrix. It gives you the confusion matrix. You see, here, these are correctly classified, sample here. These ones also are correctly classified. There's a mistake here, 10. Another mistake in this side, 1. It means this one is supposed to be here, but it has been classified as because of an error. This one's supposed to be part of this, but has been classified as this. So we have these are the mistaken diagonals. That's fine. This is default parameter. If default parameter can get to this, that is very good news. 99% for the first time. So now, if you now want to optimize, you can start your optimization, which we actually did. So you go here. The most important optimization to have to start with in support vector machine is the kernel. You have to change the kernel. If you go to the kernel, you have different options. We have polynomial kernel, we have pre-computed kernel matrix, we have PUK, we have RBF. The commonest one that haven't worked for most of the data, you can take them one after the other. Some might not even work for your data, depending on the kind of data set you have. Let's say RBF is another very popular one. So when I change this, I keep other ones constant. Okay, now I'm going to run the experiment. I'm using RBF. You see, it's running it and generating it here now. See, this is RBF, this is another kernel. Just imagine the same thing I run, the moment I click, it went through. Now you can see it took some time because this is another kernel. You see, this is another kernel. Now look at the kernel. When I use RBF, I'm trying to find the best kernel. I assume I don't know the best kernel now. So I'm going to look at the best kernel. This one is giving me 78 mistakes. 78 mistakes. You can see it. The accuracy goes down from 99 to 97. Still good, but I can see that it's worse than polynomial. So I have to do that continuously. So we have to continue to check. You have to go back again, change it to another one. So we have polynomial kernel, computer kernel. We have to keep checking each of these particular, check this one, check this one, check this one. Record your result in an Excel file as you are checking. This is called systematic optimization of the parameter. So when you hear optimization of the parameter, this is what we are doing. Very simple. And I usually encourage people to do it manually at the beginning so that they can understand how it happens, how it should work. So we keep changing it, note down the result, and then until you finish doing that. So you can see there now, we have seen the result for polynomial, we have seen for RBF, do it for others, and then see the one that gave you the best. And then you select the best one. See, usually it's part of actually what I ask. You can see here, this is going to be the score model. Let me open a file for you to see. Yeah, you can see the, yeah, this is the score model. You can see here. We tried to, when we are doing the optimization, you can see polynomial kernel, normalized polynomial kernel, PUK, RBF. So clearly we see that polynomial kernel gave us the best value, the best accuracy. So that's why we finally selected, okay, polynomial is working for us. So this is called optimization. Very simple approach. So once I'm done with polynomial, then I will go back to my experiment. I will now fix, since I find out that polynomial is giving me the best result, so I fixed it permanently now. I've gotten the best kernel. The best hyperparameter kernel has been gotten. Then I make it fixed. Then I move to the next important parameter, hyperparameter, which is C. Do I have to start checking the value of C again? I'm going to increase C from 1, maybe I can make it to be 2, I can make it 3, I can make it 4. I have to be increasing the value gradually. And then C, as I'm increasing the value, you have to run the experiment. Am I able to increase the accuracy? You can see here now, by just increasing from 1 to 2, now I'm able to get 0 error. It means all my data sets are correctly classified by just changing C to 2.0. And that is why it's very important for us to know which of the parameters are most important for each of the algorithms. Imagine if I've started my optimization from epsilon, I waste a lot of time because epsilon doesn't make a big change directly. But the best one is polynomial. Polynomial can jump your result, can make your result jump from 50% to 90%. I mean, kernel, when you select the kernel. is the most important because that's the big secret behind support vector machine. Once you are done with polynomial, you go to C. Now, by just increasing C from 1 to 2, I achieve 100%. 100%, just like that. So experiments is done. Since you get your 100%, you can just check other parameter and see if there's going to be any change. Otherwise, there's nothing you want to get. You want to get after 100% for sure. Every other values, you can see everything here is now 100%, 100%. Recall, F measure, precision, false positive rate, everything become 100%. So that is for support vector machine. This is how we do the experiment. Now, the next that was used is the J48. We go back, that is 3. J48 is a type of decision tree. We selected J48. And now we are going to see, okay, what do we get? Pay attention to this. When you run experiment, you are using at least it's always encouraged in machine learning to use at least maybe 2 or more machine learning algorithms. Because in machine learning, we do more of comparison. We want to see the one that is better. Maybe someone did this work before. Can you do it using another algorithm with better result, with better idea that can make the result better? So that's why we really try to have 2. Now we're having 2, J48. Now the question is, I want you to pay attention to this. If you use cross validation, you use 10-fold cross validation for the experiment, you cannot use percentage split for J48. It will be wrong. You are comparing algorithm using different partitioning method. It's not correct. You have to be fair to the algorithms. Whatever you do to one algorithm, you must do it to the other algorithm. If you subject them to the same data, you must subject also to the same data. There has to be fairness across board. So we have to pay attention to this. Now, so when we select the J48, you click here, you're going to see the default parameter. See the default parameter. Usually, all these parameters, there are a lot of parameters here. They are not important. They are just normal parameter, like I've explained before. Seed, the kind of number of decimal places and host of others. Then the questions people used to ask me, how do I know important parameter? The important parameters are often indicated on top here, inside this particular box here. You can see J48. These values that are set here, they are the important parameters. The same thing if you go back to support vector machine. Support vector machine also indicated those ones that are very, very important that you need to set. They are indicated there. Others are just there for other purposes, as the case may be. Let's see SCMO. You can see it has more parameters to set. You can see C is there, epsilon is there, and of course the polynomial kernel, which is very, very important for us to set. Now, so we have worked for that one for SVM. Now let's look at the J48. So now we have it already using the default parameter. You can run the experiment. You can see here, J48 is 94%. So it's having 33 errors. And this is the confusion matrix. So we still have opportunity to make it better. So because if you tune parameter for support vector machine, we change it, we try to see which one will work for it. You have to also do it for decision tree. You see? And that's why the confidence, you see, the confidence is very, very important. 0.25, you try to play with it. You see, 0.25, very, very important. And you try to play with it, try to change it, try to change the value until you are able to get better results. 0.5. So you have to keep playing with that. See, it's not, you have to keep playing with the number, you have to keep playing with the parameter until we got the best parameter for our system. So if you look at what we presented earlier, we told you that the confidence factor was 0.45 and the minimum number of objects was set to 2. So these two parameters, we set it, we were able to get, okay, this is where we are going to get our best result for the decision tree because of our time. So this is how we run experiment for each of the system. Some might want to even check, you can try other algorithms, but these are the two algorithms that this particular paper have provided us with the opportunity to demonstrate. So note that they use cross-validation. Yeah, you can see we made a mistake. We mistakenly changed this to 80. We didn't take it back to cross-validation. So this result was not valid. This result is not valid. So, you know, I was explaining that you don't use percentage split for the second algorithm when you have used the cross-validation for the first one. But I forgot to uncheck this one. So we have to repeat the experiment. We go back to cross-validation. So the two algorithms must be subjected to the same principle. If you want to use 80% split, 20% testing, you have to do it across board. You don't do it for one and do the opposite for the other. In that case, your comparison of result will not be valid. Now let's do the experiment again. This is tenfold. Yeah. For decision, we are using decision tree or stable decision tree. Yeah, you can see. So actually it's getting 95% when we use the same partition system. That's why you have to subject your system to the same thing. Because if I use 80%, 20% for it, I'm doing different experiment entirely. And you don't expect the result to be the same. And it's not going to be fair to the algorithms. In some works, some people, if they have the time, they will use 80%. They also use tenfold cross-validation. They provide all the results because they don't want any negative comment from any reviewer. So then they will now justify which one they are going to select. That is also valid. You see, you use cross-validation, you also use percentage split, and you show all the results. Because maybe in literature survey, you find out some people use percentage split on the same work, some people use cross-validation, then you decide to use the two. And you provided all the results and you give justification why this one is the final one that should be used. This is also allowed. But if you also stick to a particular one, especially, let me clarify this point. If you are the first one to run the experiment on that data set, then you are at liberty to select whatever you want. Especially if you are the first one to run the experiment on the data set, you are at liberty to select which other partitioning method you want to use. In that case, other people will follow your experimental procedure. However, if someone already worked on that data set and published the work, then you need to, for you to be able to compare your work with his or her own work, you need to use the same procedure they have used. If they use cross-validation partitioning, you have to use it. Otherwise, it will not be valid. You cannot compare cross-validation partitioning with percentage split. It doesn't work that way. Even if you like to do the two, you might do the two. Sometimes some of my students, they do both cross-validation and they also do the percentage split. Although the one in literature only did percentage split, they do the two. They now compare the result of the percentage split that is the same as the previous research work. So we have to be very fair to whenever we do our experiment, especially when we want to compare with earlier published work. Because sometimes we want to improve upon what they have gotten. There's a very nice data set where people only achieve 85% accuracy. So you want to improve upon that particular result. But then you need to follow their own procedure of data partitioning. If you like, you can add the additional partitioning method, meaning that you are doing two experiments, but the one you are going to compare with them has to be the same like their own experiment. And I hope that clarifies. So this is how to demonstrate what we've done in this particular paper. And then I want to believe the final thing is that we are now going to discuss, hopefully maybe a nice class, how do we put these results together? What are the salient points that we need to focus on when we are reporting our experiment in machine learning? We have discussed how to write machine learning paper in some of our earlier videos, which we recommended for us to check out. But in this case, we are going to look at this paper practically. What do we need to report? We have done the experiment. We have repeated it. We have achieved the same thing. Then what are the important things that we need to spell out so that we want to call the attention for our readers especially the reviewers, to important information from our experiment. There are some information we have to make sure we bring up from our experimental environment down to the paper to make it repeatable and to make it acceptable. So I think this is what we are going to have for the day regarding this particular paper. If there is, we give time for us to ask questions if there is any before we call it a day. Thank you all for listening, and then we are going to take some comments or questioning. Thank you.